Hello everyone, welcome to this second lesson under probability theory. So today we shall be looking at the contingency table first. We shall look at the complement of events still, and we shall look at how those two can be applied to solve numerical cases. Yes, so this table over here will help us to understand what we mean by the contingency table. So I'll put here A, and I'll put here A complement. I'll put here B, and I'll put here B complement. Yes, so where these boxes are intersecting, for example, where I have A intersecting with B, this box over here, I'll put A intersection B. But anyways, we are dealing with probabilities, so it will be probability of A intersection B. Where I have A complement intersecting with B, I'll put probability of A complement intersection B. Where I have A intersecting with B complement, I'll put probability of A intersection B complement. And where I have A complement intersecting with B complement, I'll put probability of A complement intersection B complement. Yes, I can as well modify this to become probabilities. So this is probability of A complement, probability of B complement. But remember what I told you, if I get probability of A and I add it to probability of A complement, I will end up with a 1. So I'll put a 1 over here to show that everything here added up will give me a 1. Similarly, if I get probability of B and I add it to probability of B complement, I must end up with a 1. So I'll put a 1 over here. Yes, so this table is going to help us get a number of events. For example, if I want to get probability of set A occurring, I will follow this direction. So if I want to get probability of A occurring, it means that I'll have to add A intersection B to A intersection B complement. That's how the contingency table can help us get various probabilities. So it means that probability of A will be equal to probability of A intersection B plus probability of A intersection B complement. If I want to get probability of A complement occurring, I'll add up everything here. So what does it mean? It means that probability of A complement is actually equal to probability of A complement intersection B, which is here, plus this probability of A complement intersection B complement. Similarly, I can also get probabilities of B and B complement. So if I want to get probability of B complement occurring, which is over there, it means that I'll add up this. I'll add up this and that. So it means that probability of B is equal to probability of A intersection B, which is this, plus probability of A complement intersection B. Then if I want to get probability of B complement occurring, it means that I'll have probability of B complement being equal to this plus this. So I'll have probability of B complement being equal to probability of A intersection B complement plus probability of A complement intersection B complement. Then of course we know that probability of B plus probability of B complement is equal to 1, and similarly probability of A plus probability of A complement is equal to 1. So actually this information is very important. It will help us in solving a number of questions. So in case you've forgotten a formula for getting a certain probability, you can always draw a simple contingency table and it can help you get various probabilities. Then I will also use this opportunity to re-echo on the complement of events. In the previous lesson, I told you that the probability of an event occurring plus the probability of that event not occurring is always equal to 1. Since the total probability is 1, it means that if I get the probability of that event occurring and I add it to the probability of that event not occurring, I must get a 1. So that's what we are going to do here. It's just a recap. So probability of A plus probability of A complement, which means A not occurring, must be equal to 1. Similarly, probability of B plus probability of B complement is always equal to 1. Probability of A intersection B plus probability of A intersection B at everything complement is also equal to 1. And therefore from this formula over here, we can see that probability of A intersection B is actually equal to 1 minus probability of A intersection B but complement, or probability of A intersection B but complement. Note that the complement is outside the brackets, it's not inside. We shall look at that case where it's inside. So I say that probability of A intersection B but complement can also be equal to 1 minus probability of A intersection B. So we can put this formula into our minds, they will help us at some point. Yes, then probability of A union B plus probability of A union B but complement is also equal to 1. And still from that, we can note that if I want to get probability of A union B, it can be got from 1 minus probability of A union B but complement. Or if I want to get probability of A union B but complement, it can be got from 1 minus probability of A union B. Yes, so that is it under complement of events. Then lastly, I want us to learn about something known as De Morgan's rules. So everything we are learning here is just going to help us simplify life as we are solving the different numbers in probabilities. So the first De Morgan's rule says that probability of A complement intersection B complement is actually the same as probability of A union B but complement. So what are we doing for De Morgan's rule? De Morgan's rule suggests that if I have A complement intersection B complement, I can remove this complement, I can factor it out. Since it's appearing on A and B, I can factor it out for lack of a common word. I can factor out, I can remove that complement from brackets so that it crosses and comes outside. But as it comes outside the brackets, this intersection will also change to, union. What am I saying? Probability of A complement intersection B complement, if I take that complement outside of those brackets, I'll have probability of A. So that it would have been intersection, but since I've taken the complement outside, this intersection will change to union, then B but complement. So that is very important and we must put it into our minds. Then we shouldn't forget that from the complement of events, this probability of A union B but complement is actually the same as 1 minus probability of A union B. That's just a reminder, we had looked at it. Yes, so that is our first De Morgan's rule. Maybe to summarize it, it is saying probability of A complement intersection B complement is equal to probability of A union B but complement. Then a second De Morgan's rule, if we have probability of A complement union B complement, as I've told you, this sign, the complement, can be factored out, and if we have a union, it will change to intersection. So that probability is actually the same as probability of A intersection B but complement. Then from the complement of events, we know that probability of A intersection B complement can be got from 1 minus probability of A intersection B. Yes, so if we are to summarize our rule, we shall see that probability of A complement union B complement is actually equal to probability of A intersection B but complement outside. So that is an important rule that will help us on a number of occasions if we are solving questions that could be involving any of these events. Yes, thank you very much for listening. We shall meet in the next lesson where we shall introduce types of events.